We will start with a new stack up here. And when you go and click new, then you just get a default stack up. And it's predefined with the most common setup, but the most common is still a pretty small percentage because we just have a high mix environment here. So 62 thickness, FR 4 material, flow construction, 8 layer build. Say it's a 10 layer or a 12 layer. We can change that easily here at the beginning. Most common is solder mask top and bottom, silkscreen. Top and bottom is pretty common, and then white. So the part of the system that we're looking at today is really just the stack up generation. So here's the very basic starting definition, and we'll add some more detail to it. Hit next. So when you give it the default or the starting configuration, you tell it how many layers. It does the math for you on trying to figure out what the individual cores need to be used and how to separate them, and it'll kind of do a first pass on trying to achieve your target thickness. We usually start out with a 1/2 ounce on an outer layer. So your internals can be all 1 ounce. You can have mixed copper weights. Depending on usually the plain layers are usually the ones that are 1 ounce. Other than the signal or the mixed layers are usually 1/2 ounces depending on the design. And then also the actual design will impact the thickness as well. So if you have a ground plane and pre-pregs is not going to fill as much as if you had signal layers and all that. So all of that does come into play whenever you're designing your gap thicknesses. As I was changing those, it was making it a symmetrical construction automatically. If I changed it down here, it changes up there. Again, that's most common, but not necessarily the case. So we have to carefully check the stack of components to what the customer provides, and then it'll give us our starting point here. Now, some of this information comes from the sales order or the quote, depending on what stage of the process we're in. You need to fill some of these things in to get the processing to work, and it's also used for different parts such as import and to other systems and for rules driving, but not super relevant to the stackup itself. 18 by 24 is our standard panel size. We build anything that we think is buildable on that. So the exceptions would be exotic materials, materials with very high scale, or just very expensive materials where the customer doesn't want the part that big. Now we're going to give this another drill layer. Let's make it a through drill. As we define the drills, they're reflected graphically here, which is a convenient reference for different parts of the production process or for layup and lamination. This gets printed out both on our travelers and as a supplemental report. You can see with the drill types, it supports different types of drills. We could do a microvia, which is defined as any hole smaller than 6 mils, typically done on a laser. Back drills and depth drills are in here. Counter bores and countersinks, slots plated. So there's lots of different types of connective structures we can put in the boards, and they're done in different processes. They may be drilled or lasered or milled or mechanically routed, but ultimately, they're all either for achieving a certain shape or for connecting the different layers electrically. So we've put some drills in here. Let's do like an 8 to 10 depth drill, just 9 to 10 depth drill. So now we have a little more going on in our stack up, and we can go into the next part of the software. And this is where you tweak things in more detail. We can change the copper weights for individual layers. And these are the suggested pre-preg constructions that come out of our library, where we define different common constructions for materials that we have available that have been found to work for achieving specific thicknesses. But you can achieve the same thickness in multiple different ways with most manufacturers' pre-preg sets. You can buy thicker pre-pregs and thinner pre-pregs and combine them in different ways to achieve the same end thickness. And so the planning process evaluates those characteristics and puts them together, depending on the right mix of maybe there's impedance requirements or very specific thickness requirements, or it's just about cost and ease of production. We can also do some impedance in here. In this case, if the target was 50 ohms and the tolerance was 5, our predicted value is 46.4. Because that's intolerance, would that typically be good enough? Changing the line thickness or the dielectric thickness can be used to kind of dial in the impedance. They're both pretty easy to change at this stage, but if you've already had builds underway, or you need to tweak something, or you're just trying to take advantage of materials that you already have for faster turnaround, then it might be easier to tweak in the line thickness. There's a limit to how far you can go with that, but impedance is pretty sensitive, so you can tweak it a pretty small amount and help to dial it in. Back to the stack up. Now we've got some impedance in here. And pretty typical basic arrangement for an FR4 base circuit board. You can see we default to using isola 185HR cores and 370HR prepregs, which is what we actually default to if we're doing FR4. And on the reporting side, the end result looks like this, where we get a summary report. In the summary report, you get some of the header information and your stack up and different specifications of the thickness, over laminate, over metal, the overall thickness, nominal, the difference of assemblies, and then finally a separate table for impedance if you have impedance calculations. Just note that if you go to the General tab, you see how that through hole is highlighted yellow. That means there's something wrong. That means you can't build it because you're trying to build it on a core construction. When you start in the middle of the core, so you would have to change like their channel or how you build with it via through from 5 to 10. So there's some built-in error checking and validation for that kind of thing. There's a lot more on the planning side, but yeah, one of the important ones is the automatic math for thickness and for drill validation. So it helps prevent some user errors like specifying an invalid drill to the types of layers that they're in, or there's some size validation that we do in different parts of it. We can't have a microvia that's 20 mils. It will also drive other logic and the planning processes in CAM and in other places. So the stack up really is the starting point for getting the job right. Everything else flows downhill from the stack up, and especially the drill definitions, because that goes into determining the drill structures we need in CAM, the coupons that we need, how many lamination cycles we need, and basically how it's going to get built. So it's an important part of the process.